Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Bernoulli P random variable. You remember that there's some, if you start with an event that has probability P, then the indicator function of that event is Bernoulli P. But you don't have to write the event specifically. You can just say x is Bernoulli P. If the probability that x is 0 has to be 1 minus P, and the probability that x equals 1 is P. That's all you need to know, because our probabilities already add to 1. That tells you what a Bernoulli random variable is. So now, binomial, to do the other ones that we're going to derive from Bernoulli, you have to have x1, x2, x3, and so on, independent Bernoulli trials. All right, now I have to figure out what that noise is. In case you're wondering what independent means, because technically I didn't define independent for random variables, I only defined independent for events. When we're talking about an indicator variable, for the event E, if E is independent of F, that's the same as indicator of E being independent of indicator F. So just think of the event where x1 equals 1 is independent of the event where x2 equals 1 and so on. Because that also means that the complementary events are also independent. x1 equals 0 is independent of the event x2 equals 0, and so on. So they're independent in exactly the sense that you'd want, but it does have to be mutual independence, not pairwise independence. So let's go on. Binomial P. I'm going to phrase it in a different form than I did yesterday. Yesterday I said binomial P is the distribution of the sum of the number of successes in the first n trials. And I'm sorry, that should have been binomial NP. Bernoulli just has one parameter. Binomial has two parameters, the number of trials and the success probability at each trial. So I'll say K has the distribution binomial NP if K is equal to just the sum. I want the sum of all the indicator variables. That will tell me the number of successes. Because by convention, a 1 is a success. We call the case where it's 0 a failure. It's just a matter of nomenclature, totally arbitrary. But just by convention, I'm going to call 1 a success and 0 a failure. And then if K is the sum from I equals 1 to n of xi, you see that that's going to count a 1 for each of them that is a success. X equals 1 is a success. And that's going to count a 0 if it's a failure. So that specifies what I said in words before, which was that it's the number of successes in the first n trials. Okay. And now, what about geometric? Let me say a random variable, I'll call it capital N, is geometric, once again with parameter P, if, last time I said it in words, so it's the number of times you have to wait until the first success. I guess I can sort of write that in mathematical notation. N is the minimum of all indices I. Now, did I ever use the boldface N before? If I didn't, it means natural numbers, which means whole numbers. So whole numbers. 1, 2, 3, etc. And it's the first one of them that actually is a success. And remember, our coding convention for being a success is that xi equals 1. Okay, so that's one definition of a geometric random variable. But the names that we give always apply to distributions. So even if you came up with a variable by a different method, but it had the same distribution as these particular examples, then you would also count it as a geometric random variable in this case, binomial in that case. There's one other that I wanted to do, which is negative binomial. N is going to be negative, I'll write out the full word, binomial, it has two parameters, k and p. And I guess I could have called it np like binomial. I like to use kp because that way in both cases, it's a convention, but that way I'm always using k for the number of successes. So, okay, so k is the desired number of successes, and you stop after that desired number of successes. And p is, as always, the success probability at each trial. Each independent trial has the same success probability. Okay? Now I said that it's going to be the, one way to think about it is you have this sequence of independent Bernoulli trials. Well, okay, n is the kth index I. We do all the indices in order 1, 2, 3, 4, 5, 6, 7, 8. We look through them all and we find the first one that gives you a success. If you're just going to the first one, that's geometric p. And that would also be negative binomial 1p. Negative binomial 1p is the same as geometric p. Just as binomial 1p is the same as Bernoulli p. Binomial with one trial is Bernoulli. So negative binomial 1p is geometric p. It's the case index I in order, in ascending order, such that xi equals 1. So I find that a little hard to write just in terms of a minimum, but you can at least see what I mean there. Case index I in ascending order such that xi equals 1. Okay, alternative definition, and you probably imagine how this comes about. If I want to wait till the kth success, I wait till the first success. After that success, all the trials in the future I haven't looked at yet, and they are just like the previous trials, they're all independent Bernoulli trials. Every trial has probability p of success. And so, if I start again waiting after that first success, start again, count until the second success, that's like another geometric. It's just starting from one above the previous geometric. So if I add up, if I actually get two independent geometric p random variables, they're independent because the trials underlying them are independent. If I add up two independent geometric p variables, I actually get negative binomial 2p. Because if I want to wait till I have some machine, I just press a button that says success or failure, and independently every time. So the geometric distribution is press the button and tell me the number of presses until you see success. Okay? Negative binomial should be press the button, tell me the number of button presses until the second success. That's actually two geometrics in a row. I do one geometric till the first success. I've done a certain number of trials, and I add on the number of trials I need to wait to get another success. That's an independent geometric. So another way to write it is n has the distribution, this negative binomial. I'm sorry about this. I'm actually going to change the name of my geometric. I'm going to write my geometric as n subscript 1, just so that I don't have two different meanings of n on the same page. And then, it's kind of neat, I can write n is negative binomial kp if it has the distribution of the following thing. N is equal to n1, so n1 is going to be a geometric like above, plus n2 plus n3. So in general, if I'm waiting for k successes, I have to play the geometric waiting time game k times. One for the first success, one for the second, and so on. Where n1, n2, n3, ... are mutually independent. I'm going to cease using the word mutually soon, but it is always implied. Mutually independent geometric p random variables. Important that they're independent because the new trials have nothing to do with the old trials. So that's another definition. So before we go on, and we have to do a lot more theory about random variables, particularly to do with expected value, expectation. But before we do expectation, let's write down the probability mass function of these random variables, because that's something we can do just using combinatorics. So let's do the PMS. So the PMFs of these random variables, first of all, I already gave you the PMF of Bernoulli P. It's barely worth writing down. It's the function that only takes two non-zero values. It takes the value 1 minus p at 0, p at 1. The probability mass of Bernoulli, so now I'm going to save myself writing effort by using that convention. Remember subscript. That capital K subscript means this is the probability mass function of binomial NP. So probability K of little k. You'll notice when I do probability mass functions, it's conventional to use a lowercase letter inside because that's just a test, that's just a number. Like, what is the probability of being that particular test number, lowercase? And capital is used for the random variable itself, so they're the same letter but lowercase and capital. This is equal to, well, it is the probability, just in case anyone was in any doubt. Remember, k is the sum of the xi's. That, well, I could say that the sum of the xi's equals little k, but that's saying that exactly k of the variables x1, x2 up to xn, those are the first n trials, are 1. Some of the trials are 1 and some of them are 0, and I want the probability that exactly k of them are 1. I don't care which k, I just care exactly k. Okay? So I'm going to lead you down the garden path a little bit, as I sometimes do, and then we'll fix it. So first of all, I want k of them to be 1. Okay, so the chance of being, they're independent trials. The chance of being 1 is p, so I want p for x1 to be 1, p for x2 to be 1, p for x3 to be 1, and so on. So I raise p to the power of the number of 1s I want, which is k. And then everything else has to be 0. The chance of being 0, of being a failure, is 1 minus p. And I have to raise that to the power of the number of failures. The number of failures is, well, there's n trials, k successes, so n minus k failures. Now what I've written yet is not yet the probability that exactly k of them are 1. It's something slightly different. Can anyone explain the difference?
There are different combinations of which ones could fail.
Exactly. So, and in fact, you'll notice when I said that, I even said, let's figure out the probability that x1 equals p, and then x2 equals p, and so on. So this, what I wrote down so far is just the chance that the first k of them are success, and then the remaining n minus k of them are failure. That's only one way that it could happen. There's a whole lot of other ways, and as you said, the exact number of ways it could happen is the number of combinations. A combination is a way of writing the letters f and s for failure and success in some order, such that there are k successes and n minus k failures, and that is, of course, n choose k. So, okay, so we figured out the probability mass function of the, so in case anyone forgot, this is binomial, sometimes I'll abbreviate NP, pk of k is equal to this, so I can even, that's the first one. Now, let's do the second one. The second one is for geometric, and I'll use N1 as I've been using for geometric. That's going to be a little bit too dense. N1 has a geometric P distribution. Now I want the probability that N1 is equal to some specific value N. Okay? So remember what that means. The first time that you get a success is on the nth trial. That actually tells you everything about the pattern of successes and failures, doesn't it? Can someone tell me, if I know that it takes 3 trials to get the first success, then what was my pattern of failures and successes? Yeah, F, F, S. It had to be. You couldn't have any S's before the third. So you know exactly what it is. It has to be, everything is a failure before the success. So there's no combinatorial term. There's just failure, failure, up to n minus 1 of them are failures, and then the nth is the one that is the success. As I say, the convention we use is that you include the success. So I don't even need to put the power 1 there. So it's just optional. So 1 minus p to the power n minus 1 times p. Now, by the way, a property necessary property of PMFs is that they always add to 1. Now, the fact that this one adds to 1, you can go through and check that's the standard summable geometric series for a positive common ratio of 1 minus p. And this guy, it's not the geometric series, it's actually called the binomial series. It's a finite series for, it's really just a binomial sum, like in the binomial theorem. Although, dating back to Newton, there is an infinite version of the series which works when n is not an integer. So for us, n is always an integer, so you only need a finite series. So that's why this guy adds to 1, it's just the binomial theorem. And then finally, let's do in total, which I'm now using to refer to negative binomial with lowercase p. So you see, if you don't get your lowercase and uppercase separate here, you're going to be a bit confused. Because lowercase is values that you substitute in, and uppercase is variables. So random variables. So p subscript capital N of n. So it's the probability of getting your kth success on the nth trial. K is fixed. You have to get up to k successes. I wait until that kth success happens, and n is the random number of the trial on which it happens. And so there have to be k successes, right? Because I'm waiting till k successes. There have to be n minus k failures. Because after all, n is the total number of trials after you get to the k success. So this bit looks very familiar. Once again, it's not just that without any factor out the front, because that would be what happened, I guess, for some specific ordering. I guess you'd probably want the ordering the other way around. You'd probably want n minus k failures first, and then k successes, and then you would stop on the k point. But that is not the only way it can happen. With geometric, there's only one way it could happen. You have to have the single success at the end. For negative binomial, you're looking for the kth success. So, of course, the kth success has to be at the last spot, right? That guy is fixed. This is the kth. The kth success is in the last spot fixed. And then the rest of them are jumbled up. I'll just put X question mark, because it actually, any ordering of the k minus 1 failures and n minus k successes, k minus 1 successes and n minus k failures there would be acceptable, so long as the kth success happens at that point. So can anyone tell me, and it's probably not giving much away to say that it's a binomial coefficient, how many ways are there to choose a valid ordering, remembering that the kth success has to be at the last spot, so that's not part of the choice? Yep. Well, k minus 1 is what you're choosing out of. You're choosing k minus 1 successes. Yes. And I have to choose it out of how many total trials? N minus 1. Yeah. By the way, it would be the same to say n minus 1, choose n minus k, of course. So that's negative binomial. It doesn't look quite the same, but of course, here, if you were to, so you might ask, how do they both sum to 1? Well, it's a totally different question, because for k fixed, you're summing over n here. So it's a fact. It'll be, by the way, negative binomial can be as high as you like. It's an infinite series here. So there's an infinite series of that form, which actually fits into, the reason for negative binomial, if you're wondering where negative comes into it, the negative doesn't come from minus 1. The negative comes from the fact that if you fiddle around a bit, you can write it actually as the Newton series for 1 plus, or p plus 1 minus p to the power minus n. There's a Newton series for p plus 1 minus p to the power minus n, but unlike positive powers, the negative power expansion goes on forever, and that's why it goes on forever, the number of terms. So that's kind of that's irrelevant, you don't really need to know that. But that's what negative binomial is all about. It's an infinite, there are infinitely many possible values. By the way, what is the smallest possible value of negative binomial kp? Number of trials up to and including the kth success. So it can't be 0. Geometric could be 1. because you could just get a success straight away. But what's the minimum possible value that negative binomial could take? Yeah, if it was negative binomial 2p, it would be 2. If it's kp, it's k, because that would just be having all the successes in a row. That would be quite unlikely. The probability would be p to the power k. And then you would be left over with 0, choose 0. Or okay, whatever. You'd have k minus 1, choose k minus 1, which is 1 times p to the k. So that's quite unlikely. Normally it's more likely to be higher. The exception is geometric. The most likely value of a geometric is 1. It's a decreasing one, but that's different for other ones. So we've done probability mass functions. We now definitely need to do some more theory. And that theory will tell us about expected values. So, and then once we do that, we can, because really unfortunately, although we've already defined probability mass functions, we've kind of exhausted a lot of what we can do using them. So we're going to go back to theory, and then that will allow us a lot more powerful techniques. So expected value. Okay, so there are some difficulties in the definition, and I'll sweep over some of those, because essentially expected value is a uniform concept that makes sense for all random variables. But although the concept makes sense, it may not actually exist. And we'll talk about some of the cases where it does not exist. But nevertheless, what is the concept? Okay. Concept of expected value, which is sometimes called expectation. Well, before I say it, any thoughts from the audience? This is just descriptive. Apart from the visibility. Any other thoughts? I roll a die. Oh, well, let's do an easy one. Flip a coin and let's make it an indicator function of tails. So it's 1 if it's tails and 0 if it's heads. Then what is the expected value that I get? Well, to some extent it doesn't make sense, because half of the time you get 1, half the time you get 0. You don't really expect to get either of them. It's equally likely. So let's make it kind of more concrete and say if I bet $1 on every tail, not increasing the bet, let's have a stake of $1 for every tails. So in theory I could, and then I do it 100 times. I could win $100 if I got tails every time, or I could lose $100 if I got heads every time. What would I expect? What would be my expected winning? 0, yeah, it's a fair game. That would be an expected winning to 0. So clearly the expected winnings of 0 is not saying that every time you run the game you'll get 0. In fact, it's not even saying that most of the time that you run the game you'll get 0. So that would be, you'd get 0 if it was 50 heads and 50 tails. But we can even figure out the probability of 50 heads and 50 tails offhand, just because I know the formula. It's approximately 1 over 20, 1 over 10 root pi. So, 1 over 15. So it's not particularly likely that you get 50 heads and 50 tails on the dot. That's not particularly likely. But you are likely to be around it. It's also very likely to be 49 or 51, and it's still quite likely 48 or 52. And then once you start wondering about the probability of getting 60 heads and 40 tails, that's quite unlikely. And 70 heads is so unlikely as to be barely possible. And if you actually got 70 heads, just like any sensible person, you'd start thinking, is this actually a biased dart, a biased coin, because it's vanishingly unlikely to get 70 heads out of 100 if you do it with a fair coin. So that's one of the powerful things that we'll do using independence later. So it's something to do with kind of winnings, but it's not what you always would get, and it's not even what you would. It's something that you'd get close to if you repeat the experiment a lot of times. So this is starting to sound a lot like what I said with the law of large numbers. And lo and behold, although I haven't defined expected value yet, it's not giving anything away to say there's a version of the law of large numbers that says the long-run average of doing a same experiment many, many times. And remember, the first time I talked about the long-run average, I was talking about long-run proportion. So that was just long-run fraction of times that something happens. We know that tends to the probability. So if I instead have a numerical experiment with an average value, then the long-run average of the like if I do die rolls, 1 to 6, what's the long run average of my die roll? 3.5, because, well, you can see that symmetry. It's sort of equally likely to be 3 is 4, equally likely to be 2 is 5, equally likely to be 1 is 6, and each of those averages out to 3.5. And so we'll be able to calculate that in a moment. Yeah, it's not 3, of course, because it's not symmetrical, about 3, 3.5. So it is something along the idea of a long-run average, but once again, that will be a bit motivational. So long-run average of... Now, the key thing about the trials, expected value, it has to be of a random variable x. Okay? So you have to have a random variable. It has to be a random number, not a letter or anything, to have an expected value. The long-run average of many independent and, now this phrase will come up many times, identically distributed, so much so that we have an abbreviation. Trials, okay. So those are called IID. The standard abbreviation for independent identically distributed is IID. Long-run average of many independent and identically distributed trials of, and I'll call each trial, in this case I don't mean a trial as a yes or no, it'll actually be an outcome of a particular experiment, and I repeat it independently, each of which has the same distribution as x. Okay, so it's really about the distribution of x. And I put this in inverted commas because that's not a mathematical definition yet, but it gives you some idea of what we're doing. Now, if we have a discrete random variable, x, and let's just say, let's even say with finitely many values. This would be the very simplest case, finitely many values. So p x of, okay, so it can take the values x1 is p1. If it only has finitely many values, I'll just write them out even like this. So x, I don't really care how many possible values it is, it's not that important. I'll say n, okay, pn. Now, if these are the only possible values, by the way, some discrete random variables have countably many, not finitely many, so I'm being even more restrictive. x1 up to xn. Okay. Here's the deal. I'm going to use this inverted commas statement that I made to come up with a sensible definition of expected value. Okay. We expect, so in capital N trials, so that should be a large number of trials, we expect, okay, here's that word expect again, approximately, now it's not going to be exact, but approximately, through what we talked about at the start, that it's like approximately the long-run proportion of the trials in which you get this specific value, that long-run proportion is P1. So we expect approximately NP1 x1s. Does that make sense? Like, I've only got these finitely many values. Think of a die. Your values are 1, 2, 3, 4, 5, 6. Then you've got the values 1, 2, 3, 4, 5, 6. I do it a large number of trials, say 6 million trials. I expect 1 million ones, 1 million twos, 1 million threes, 1 million fours, 1 million fives, 1 million sixes. Now, it won't be on the nose. The chance of being exactly on the nose of 1 million is low. But it will be around that. And we even have that law of large numbers that says the limiting fraction, that limit tends to 1/6, the probability in the case of a die. So it won't be exactly there, but it'll be around there. So that's why I say approximately NP1 x1s and NP2 approximately, and none of these will be exact necessarily, x2s, and approximately NP3 P n x n. Right? So that's what we expect of each trial, and so we expect a long-run average. It's all about the long-run average. That's what we're trying to think of. Approximately. So there'll be. Now, to do an average, you have to add up each measurement. Add up all the measurements and divide by the number of measurements. There were capital N measurements, which is going to be huge. And we have NP1. That's the number of x1s I expect. So that's the number of x1s, and I have to multiply that by x1. So NP1 x1 plus NP2 x2 plus dot 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 plus NP. Now I've got a lowercase n. I hope you can manage that. Lowercase n was just a fixed number, which is the number of possible outputs of this random variable. Capital N is a very large number tending to infinity, which is the number of trials. So, now, while that's what we expect of approximately, okay. It's an approximation because each of these counts of trials was an approximation. It's not necessarily that. But the long-run average should then be, all the n's cancel, of course, so that is P1 x1 plus P2 x2 plus, so that would be sum I equals 1 to n of Pi xi. That's exactly what it is. The probability times the value you add up over all possible values. That's what you expect. Now, this really, I'm going to take that thing about long-run proportions. I just want you to take it as granted, even though we haven't proved it as a mathematical theorem. It conforms to our intuitions, and it is certainly true. So the thing about these approximations, I'm now going to say something a little more higher order. You might say this is worthless because it was all based on an approximation. But actually, if you were to be a bit more precise about this, you'd say that not only is it np1 x1s, the fraction np1 divided by n, the exact fraction tends to p1 exactly. And the exact fraction here tends to p2 exactly. So as n gets larger and larger and larger, the expected long-run average gets closer and closer and closer to this. So there's no other possible value. It's not like the expectation is approximately this. The expectation is exactly this. If you want to get closer and closer to this, you just bump up n as high as is needed. So this is exactly the definition. And then, so this is actually the definition of the expected value of x. So we introduce a new, nice, double-barreled e. Now, unfortunately, there's various levels of slovenliness that are used. You can omit the brackets if there's no confusion. And often the letter e, even not boldface, is used. That can be a little more confusing. But you can do some combination of that. So I try to make it a bit more ceremonial by putting boldface and brackets, but you don't have to. So that's what the expected value is in this particular case, a discrete random variable with finitely many possible values. Now, I'm just going to even rephrase that. The rephrasing can be really useful. Okay? So a variable that can take a certain number of possible values, especially if it's only finitely many values with specific probabilities, that is a linear combination of indicator variables. There's a reason that I introduced those. Any such discrete random variable is a linear combination of indicator random variables. So sum of I equals 1 to... I'll use n, although n doesn't have to be the same n as before. I want a linear combination of indicator variables. If anyone hasn't seen the word linear combination, it means sum of scalar times vector plus scalar times vector, or scalar times function plus scalar times function. So in particular, scalar times indicator function. So the scalars are actually these values that are taken. So let's take the value xi, x1, or xi on event I. So there are a whole lot of events ei, and a whole lot of values that you take on those events. Equals Oh, so that's just a random variable that's obtained by adding up lots of indicator random variables. If I want to take the expected value, I get, well, my definition will be that this is defined to be xi times some, no, I have to put the xi inside the sum. I'll do it on the next line. Equals sum I equals 1 to n of expected value of, well, I want this to be a definition. Sorry, so, okay, I've got, as a definition, I'm going to put xi probability, this will be xi times probability of ei. So in other words, you have a number of values that you could take xi and a number of events on which it takes those values. So that's like event x1 with probability p1, event where you're xn with probability pn. You add up the values times the probability of the events. That is the expected value of the sum or linear combination of indicator and random variables. And a particular case that is often useful is the expected value of the indicator of some particular event, E. So E will be an event here. I'm going to just make that bold so it's not that confusing. Here E is an event, and the boldface E is the expectation operator. The word operator is a fancy word used because it's like the integral sign. In fact, we'll get to that later, or a summation sign, an operator that puts together produces a number from a function. So the expected value of the indicator variable on an event E, I know this is kind of abstract, but can anyone figure out what that is going to be? Remember, the indicator function of an event E is certainly a discrete random variable with finitely many possible values, and in fact it only has two possible values, 0 and 1. So what is the expected value? P of E. Yeah, someone said P of E, that's right. Because on the event where E is true, you get 1. So P of E times 1 plus 1 minus P of E times 0, but the 0 term you don't even have to say. So that's even worth remembering as a separate formula. Expected value of an indicator variable is just the probability of that event. And it's linear. We're used to lots of linear operations. Linear is a fancy way of saying you can split over sums, you can split over differences, and you can bring constants out the front. That's definitely true of the expected value operator. So the expected value of the indicator of an event E is the probability of E. So already, you'll notice we haven't yet defined expectation for all random variables, only for discrete random variables with finitely many values. But already we can use this definition that if we have a die roll, D is equal to, 1, 2, 3, 4, 5, or 6. Of course, there are other dice, but I'm always talking about six-sided die with probability 1/6 each. Okay. The expected value of D is exactly as was said before. Sum I equals 1 to 6. Those are the 6 possible values. Probability times value, or value times probability. Doesn't matter which way you do it. So 1/6 is the probability times the value, which is I. It takes the values 1, 2, 3, 4, 5, 6. So that's 1/6. It's actually the 6th triangular number, I guess, if you like it, 21. So it is 3.5 as foreshadowed. Okay. So, and what about the expected value of, if you have a fair coin, these are the two ones we use all the time. If you have a fair coin, what is the expected value of, by the way, you shouldn't really say the expected value of the result, because the result is head or tails and they're not numbers. So we should say expected value of numbers. But I can do the indicator function of tails. Okay, that's kind of here. It's just indicator function of the event that you come up. Tails is
0 and 5.
Yep. So as always for indicator events, that's probability of the event tails, which is 1/2. So as you'd expect, your score is on average a half. Why is that different from that game where I said you expect? So in terms of the bet, if you bet $1 on heads or on tails, or let's say on heads. It's not the same formula as there, because then you lose the dollar if you lose it. So that is the random variable of winnings. Your winnings for one round is equal to W1, which is equal to 1 with probability a half and minus 1 with probability a half. Okay, so that's because you lose your stake if you lost the bet, and so the expected value of W1 is equal to 1 times a half plus minus 1 times a half. So the two possible values times their probabilities, which is 0. So now let's combine that into many more terms. In fact, I want to prove some big theorems about the expectation. Before we even calculate, so the only variable we have so far calculated the expectation of is a Bernoulli, because Bernoulli P has expectation P because it's the indicator function of an event with probability P. So we know the expectation of Bernoulli. We don't know the other ones. So let's do the theorems before I go on. Theorems. Now I'll call them theorems because we've done about E, and these theorems are actually true whenever the expectation exists. So the proof that we'll be able to give will be we've only done it for a subset of discrete variables, those discrete variables that have finitely many values. So we've only done it for that small family of variables. The theorems turn out to be true whenever the expectations exist, but we'll be able to prove them for that subset for now. So the first one is that, and some of these will just be facts that we've already done. So expected value of a constant is constant expected. So these will just be properties that you'll need to use all the time. So that constant, what does a constant mean as a random variable? It's the random variable that's always the same value. It's C with probability 1. So expected value of indicator of an event. We already had this, but that's probability of that event. If you have expected value of, so now we're getting into the big ones, of a constant times and a random variable is equal to the constant times the expected value of the random variable. Okay. And 4 will have to be about sums of random variables, and the differences will be actually the same, so I'll just put it in the same. So if you do x plus y, that's expected value of x plus expected value of y. I can't overstate how important these theorems are. And they seem kind of abstract, but they allow you to solve a lot of problems. A real thing to note about this one is we do not need independence of random variables. I haven't defined independence of random variables yet. But regardless, you know that there are variables that can be dependent, like even the same variable twice, or something that really depends on the knowledge of the previous one that is positively correlated. In that case, it's still the case that the expectations add up, and that can solve a lot of difficult problems. Okay, and then the same, you'll forgive me for just putting a minus sign. So if it's x minus y, then the expected value is x minus y. Now, I just have to put, I know this is a little heavy because I really want to get into this before the end of the page so that I can have all my theorems before. So within this, I really need the following definition. It's been foreshadowed long enough, which is that random variables x and y are independent, okay, which is, once again, you can write that symbol, if the following is true. We already know the definition of independent events, okay? So a very simple definition for all intervals. Now, why do I keep talking about intervals? Okay, actually, if it was a matter of discrete random variables only, we'd be good enough just talking about points. We could say for every points x and y, the probability of x equals x and y equals y is the product. So that would be enough for points, for discrete random variables. we always have this problem for continuous random variables, points are not enough, so we just do it for intervals. If for all intervals, I and j, so they're just any, connected sets of real numbers, the following holds. X being in I is one event, and that we already know about independence of event, is independent of the event Y is in J. So for discrete random variables, that comes down to just the values of X being independent of the values of Y. Okay, so now I've given you the definition of independent random variables. There are other characterizations we'll get to later. Now I can state the fifth theorem, which is in some ways the nicest one. The expected value of X times Y is equal to expected. Now I should put the proviso at the start, but the big proviso in red, provided, okay, this is not true, cannot be assumed to be true unless X is independent of Y. So independent random variables have their expected values added. It is not true for non-independent random variables. I'll give you a totally simple example. There's plenty of random variables that are symmetric, positive, and negative, right? So a random variable that's symmetric, positive, and negative must have zero expectations by symmetry. You just swap all the positive values with negative values that exists. So, for instance, that plus or minus 1 for winnings, that plus or minus 1 is symmetric. So it would have expectation 0. But then if you did x times, if you just let y equals x, that's legit, then expected value of x squared must be positive, because x squared is positive. So you'd have positive equals 0. So that's clearly not true, and it's because x is not independent of itself. So this expectation of a product is product of the expectations is going to be true only when x is independent of y. So I don't have time to prove these here. Let me just do the consequences for expected value of binomial. Okay, so if we did it before, capital K is binomial NP. The expected value of capital K is equal to we know that K is the sum, I equals 1 to n, of xi. Remember we had those Bernoullis? Sorry. If you go back to the definition, we had all those Bernoullis, and that is equal to the sum of, so we've now used theorem 4, I guess multiple times, about expectation of the expected value of xi. Now each xi is a Bernoulli p, so that's sum I equals 1 to n of p. Because we know that each xi, they're all IID Bernoulli p. Okay, so that is equal to np. So if you have n trials with probability p of success, your expected number of successes is n times p. Sounds about right. Sounds a lot like that law of large numbers that we talked about, although more is needed, because just because there is an expectation, that doesn't mean it's actually the long-term limit. Turns out that that is the long-term limit as well. Next time we'll find the expectation of geometrics and also prove the theorem. Thanks for your attention. By the way, it's also relevant to this winnings, just because I had winnings on the thing here. If you did winnings on 10 rounds, you expect to win 0 on each round. Therefore, your expected winnings on over 10 rounds is also 0. You add up all the individual winnings. Same thing. Well, these are definitions even so far. Well, okay, given definitions of theorems. You totally need to know these theorems because you use them all the time.
I moved up like in the first lecture with the axing of probability. So
Yeah, that was really the flavour of it. It's not a big deal.
like, so most stuff's going to be a little bit more practical. Like,
Yeah, I mean, I'm not going to give a categorical thing. In principle, everything we cover in the lectures that I don't say, this is specific enough to discuss. But you'll find, yeah, in practice we'll be using these, well, they're really the laws of expectation we'll be calculating on.
so not master 1.5 kind of that. Like,
I haven't taken that course, but I don't know.
like analysis would be kind of.
It's not epsilon delta. No. Yeah, but I mean, you probably, what is 2.1.5?
Master 1.5 is the first year math as
But it
basically
doesn't do
analysis.
measure theory.
No, it doesn't.
Yeah, well, we also don't invent the basis of it. Same. So, yeah, I'd better get out of the way here. Let me just, I'm just going to get my, get thing out. No, I don't even have my, I didn't plug it in. Okay, I did, yeah.
You may want to roll that.
Maybe.